Okay, so in this video, I'm going to show you how to solve binary knapsack problem using backtracking algorithm and lexicographic method. So let's start with an example. The game has a shop with various items, and each item has 5 information attributes, namely ID, price, power stats, health stats, and speed stats. We as players want to buy all the items available as long as our money is still available, where we have priority to buy items that maximize power stats first, then health, and finally the speed stats, right? So I have this nested list of items that we can buy in the store. It has 5 elements. The first element is the ID, the second element is the price, the third element is the power, the fourth element is the health, and the fifth element is the speed. And then we have our available money. Alright, so what is binary knapsack problem or 0 or 1 knapsack problem? So this is a problem where you are given a set of items, each with a weight, which is our price, item price, and a value, which is our stats, right? 3 stats, and a knapsack, which is like a bag or backpack with a maximum weight capacity, which is our available money, right? The goal is to determine the most valuable combination of items to include in the knapsack without exceeding the weight capacity, without exceeding our available money. Each item can either be included or excluded, hence 0 or 1 or binary. Since we have priority to maximize power stats first, so we use a lexicographic method where multiple criteria are considered in a prioritized order. Solutions are compared by evaluating the most important criterion first, which is power stats first, and if there is a tie, power stats value has a tie, the next criterion is considered, which is health stats, and so on, and then the speed stats, right? This method ensures that the highest priority objectives are satisfied first. Okay. And today I'm gonna be using backtracking algorithm, right? So this technique used to solve problems incrementally by building partial solutions and then abandoning them if they are not suitable. It involves exploring all potential solutions using a depth-first search approach, where each step represents a decision that extends the current partial solution. If a decision leads to a violation of the problem's constraints, the algorithm backtracks to the previous step and tries a different path, right? So the backtracking algorithm actually explore every possible solution in the binary search tree, right? So it explores all and every possible solution, right? So, well, it can be not too efficient if we have too many items to consider, right? But if we have only like 10 items, well, yeah, we can use backtracking algorithm, right? So let's start with sort the items first. So we use we sort items based on their stats to price ratio in descending order, right? So this is power stats to price ratio, this is health stats to price ratio, and then this is speed stats to price ratio, right? And then we order it in descending order. Then we initialize variables to store the optimal solution. So this is the best value for stats, and this is the best items for in which we choose that item, right? Okay, now this is the backtrack function where we actually using recursive function. This is a recursive function to explore all possible combinations, right? So it explores all possible combination of items that can be selected given the constraint of the problem, that is available money, right? So we have IDX, which is index. This is the current position in the list of items that is being considered. And then we have value. This is a list representing the current total stats, that is power, health, and speed of the chosen items. And then we have items chosen. This is a list of items that have been selected so far. And then we have money, which is the amount of money left to spend. And then we use this global because we want these two variables to be used both inside and outside of the function. And this is our base case. So if index equals to the length of the items list, which is 10, it means we have considered all items. We then check if the current value, so total stats, is better than best value. If it is, we update best value and best items to the current values, right? Next, we see this is a recursive case where if we haven't reached the end of the list, we consider the current item. So we check if we can afford the current item. So if money minus price is still bigger than or equals than 0, we do the recursive function, right? So we backtrack. If we can afford it, we recursively call backtrack with index plus 1 to move to the next item, updated value to include the stats to the current item, updated chosen items to include to the current item, and updated money to subtract the price of the current item, right? We also call backtrack without selecting the current item to explore that branch of the decision tree, right? So value, items chosen, and money still has the same value. And then we start searching from index 0, right? We call this with index 0, no initial stats, no items have been selected, and total money available left to spend. And then we print the sorted items and the optimal selection of items and also the best stats, right? So let's run this. Okay, so here we got items after sorting by stats to price ratio, right? And then we got the optimal selection of items, and then we got the best stats. Now, maybe you see this, the items with ID 3, why we don't choose this, right? Because we want to maximize the power stat first, and then the health stats, and then the speed stats. Uh, the optimal selection would be we choose the item with ID number 10, because if we choose item ID number 3, then we should choose item ID number 5. But if we choose item ID number 5 and number 3, uh, we don't actually maximize the power. Uh, we maximize the power stats, but we don't actually maximize the health and speed stats, right? Compared to this, if we choose item number 10. So that's it for this video, and thank you.